telling you about inductors in my last lecture, and we came up to this point that we first considered a pure inductor switched on to a fixed voltage, what will be the current response, how energy can be stored, and what is the expression of the energy. Then I started discussing this problem. Okay, a series RL circuit, switch was opened for a long time. Then these are the conclusion immediately I draw. Okay, I 0 minus 0 at t equal to 0 switch is closed. So, better draw the circuit for t less than 0 and t greater than equal to 0. Always try to do that at least at the beginning, so that you do not make any mistake. Therefore, here I t must be 0, because open circuit no current can flow exist here. Therefore, for circuit for t greater than 0, of course, a source is connected across two elements in series, one of which is energy storing element L, and there we expect some current to flow, and maybe that current is a function of time, because L is present. So, voltage drop you write meticulously and correctly, write down the KVL here, you get this equation. Now, how to solve this equation? This is a first order linear differential equation. What happens is this, if in a circuit there is only one energy storing element, it will always give rise to a first order equation. In general, if two energy storing elements are there, it will be, say, inductance and capacitance both are present, then it will give rise to a second order differential equation and so on. I will do a general treatment on differential equations maybe after few lectures hence, but for the time being to solve this circuit it is very simple. Let us see, and I will do it like this. So, we got this equation. See, this was my circuit, and do not forget to write that this circuit is at t greater than equal to 0, and this was R, this is L, this is E, and this is current at any time t. This is a constant voltage, constant battery. So, we got that L di dt plus R I is equal to E. Now, right hand side is constant. So, what we do first is we divide by L. So, this is R by L into I is equal to E by L, that is what, divide both sides by L. Then these numbers R, L and E are constant. So, this constant plays a crucial role in solving the differential equation. What you do is this, you integrating factor, later we will learn several techniques to write down the solution straight away. From this straight away write down the solution, that is also possible, we will take up that. But for the time being, let us start from basics. Integrating factor is e to the power R by L into t. Multiply both sides with this. So, it will be e to the power R by L t di dt plus R by L was already there, e to the power R by L into t I, and this will be equal to e to the power L into e to the power R by L into t. This will be the thing. Is not. Now, if you look at these terms on the left hand side, this is nothing but product of differentiation of product of these two functions, e to the power r by L into t into I, and this is equal to E by L into e to the power r by L into t. That is the first function into differentiation of the second plus differentiation of this function r by L into e to the power r by L into t into the second function. So, that is fine. Now, in the next step what you do, you bring this dt on the right hand side. It will be like this. My goal is to find out I t. Therefore, I will integrate both the sides now. I will integrate both the sides. Okay. Now, if you integrate both the sides, then without any limits I am putting. So, there must appear some constant a, integrating constant, is not. Now, the integration of the left hand side will be because this itself is the differential. So, this one only, and on the right hand side it will be E by L is constant, and integration of this one is e to the power m x by m. So, it will be r by L into t by r by L. This will be the thing plus of a, of which this L goes. So, this will be equal to E by r into e to the power r by L into t plus a. This will be the thing. I have to solve for I t, therefore, I multiply both sides by e to the power minus r by L into t, both sides. Then left hand side I will be left with only I t, and this will be equal to E by r plus a into e to the power minus r by L into t. This will be the thing, solution. Now, here this constant comes in a. This constant is to be determined from the boundary condition. What was the boundary condition? We know that I 0 minus was 0, because before switching nothing was connected, and this must be equal to I 0 plus, which is as good as I 0. So, current at t equal to 0 will be continuous. So, applying that I 0 is equal to 0, from this we get 0 is equal to E by r plus a, or a is equal to minus E by r. Therefore, the solution will be I t is equal to E by r minus E by r, a minus E by r into e to the power minus r by L into t. This will be the solution, E by r into 1 minus famous equation r by L into t. So, the value of the current at t equal to 0, if you put, it is 0, because e to the power 0 is 1, 1 minus 1 0. Then it will grow exponentially. So, if I sketch this current here, it will be like this t. What the circuit was doing, and this axis is I t. For t less than 0, current was 0. It is always better, always draw the current waveform for t less than 0 also. Then at t equal to 0, you do the switching. Obviously, if you put t equal to infinity, the I as t tends to infinity, this current will be only E by R. Why? Because this term vanishes then, e to the power minus R by L into T will vanish. As T goes to infinity, e to the power minus R by L into T tends to 0. So, you know, you draw a horizontal line there whose magnitude is E by R, and then this current will is a famous curve, you know, it will grow, and asymptotically this curve will meet this final current E by R. This equation is E by R into 1 minus e to the power minus R by L into T. This is how current through the inductor will grow. Now, the question is about this t tends to infinity. T tends to infinity, really I have to wait for infinite time, that means years after years, so that the circuit current will be E by R? Not really. This time, if you say this ratio, if you define this ratio L by R by a variable called tau, which is called time constant, I am going to give you some physical insight into it, time constant, then the equation of I t can be written as E by R into 1 minus e to the power minus t by tau, is what L by R is the time constant. Now, suppose you calculate the current at t equal to tau, what is the significance of this time constant? Suppose I say I will calculate the current at t equal to tau, L by R will return you some number, okay, and its dimension will be time, that inductance by R, it will be time. So, anyway at t equal to tau, I will say I at t equal to tau after one time constant, the value of the current will be E by R into 1 minus e to the power minus 1, and this value is some 63.2%. Now, it will be about 0.632, check this number, about 63% into E by R. So, what happens is this, this current, we have seen that it is growing exponentially. At t equal to tau, E by R is this much, 63.2 of E by R, about 63% may be here. This point is 0.632 E by R, 63%, this level, and what I am telling, this is t equal to tau. At t equal to tau, it will be like this. This after this much second, current assumes it is 0, I think let me write it clearly, 0.632, 0.632 or 63.2% of the final current. That much 63% will be achieved after one time constant. One can calculate in this way, after 5 time constant or 2 time constant, you will find it will reach almost 90% or so. After 5 time constant, it will reach 99%. Therefore, although it asymptotically mathematically means you need not have to wait for so long a time to see that conclude the circuit has reached steady state. After few time constants, circuit will assume for all practical purposes E by R magnitude, final current. Okay. So, that was the thing. Now, I have sketched this current I t against time when an RL circuit is switched on. Another variable I should also sketch, that is okay, with time how the voltage across the inductor VLT changes. We know VLT is equal to L d I dt. The way I have assumed the direction of the current, it is I t. So, this voltage potential of this point with respect to this is L d I dt. I already know it is equal to E by R something. So, let me write it here. So, we have seen that I t is equal to E by R by 1 minus e to the power minus t by tau, and tau is the time constant, tau is L by R. Then voltage, how voltage across the inductor changes with time, voltage across the inductor how to find it out? I can easily VLT, suppose this is nothing but L d I dt. So, L d dt of this quantity, that is E by R into 1 minus e to the power minus t by tau, this will be the thing. Now, if you differentiate, the first term is constant, it goes. So, it will be L into d dt of minus e to the power minus t by tau into E by R. E by R is there, is not? This will be the thing. So, E by R can be taken outside. So, it will be E L by R. And d dt, let me be first minus e to the power minus t by tau, this will be the thing. So, this will be equal to E L by R. If you differentiate it, it will be minus 1 by t, that is plus 1 by tau into e to the power minus t by tau. So, but tau is equal to L by R. So, you put that. Okay. So, here for tau is equal to L by R, L by R. Then this R goes and this L goes, and it will simply become E into e to the power minus t by tau. And this is what? This is equal to voltage across the inductor. So, we found this is the expression for the current, and this will be the expression of the voltage across the inductor. So, if you sketch them one above the other, that is I sketch it like this. I t in the circuit, it will be like this, and also I would like to sketch VLT against time. So, I t we have seen it will be like this, final value will be E by R, and it will grow exponentially with a time constant tau. Now, and before that it was 0 here. As I am telling, this is t equal to 0. Always try to sketch the current before t equal to 0, at least at t equal to 0 minus what was the current. And now voltage across the inductance. So, voltage across the inductance, before that there was no current in the circuit, open circuit. So, that was 0, but at t equal to 0 V L, at t equal to 0 minus it was 0, but at t equal to 0 plus, put t equal to 0 here, the voltage will be E into e to the power minus 0 by tau, that is equal to E. Therefore, voltage across the inductor will have a sharp jump at t equal to 0. It will grow up and then it exponentially decays. There is no DC term plus to it. So, it will decay exponentially, sorry. Also this is asymptotically it will decay and it will be like this, going to 0 finally. Got the point? And at t equal to 0, this value is E. So, this is the thing, that is an RL circuit, If you close the switch at t equal to 0, RL, the inductor current cannot change instantaneously, but look at the voltage waveform. Voltage across the inductor t equal to 0 minus it was 0, but at t equal to 0 plus it has gone up to E. So, voltage across the inductor can have a step jump, no problem, it will grow up. And with what is the equation of this? Equation of this is once again this is sorry E into e to the power minus t by tau. Therefore, once again you can at t equal to tau you can find out the voltage by what amount it goes, time constant, etc. But the point I want to make is finally, voltage across the inductor is 0 and it has to be, because final current becomes a constant value E by R. So, d dt of E by R is 0. So, that is what is expected, but the voltage across the inductor can have a step jump. So, conclusion is current through an inductor cannot have a step jump. We will see there is exception to this rule when we take impulse function, impulse voltage applied, etc. But similarly, voltage of course, for an inductor can have a step jump, no problem, step jump. So, in this example also we have been able to store energy in the circuit, is not? E by R is the final current, but if you want to sustain this current in this circuit in this way, there will be additional power loss always taking place in R. Got the point? So, I want to tell you, you can do one thing. The same circuit, to charge the what people say is that I have to pump current into the inductor. Why I have to pump current in the inductor? Because I want to store energy in the inductor, because expression of the energy stored is half Li square. So, somehow inject some current into the inductor. You have to apply some voltage, etc. Now, the same circuit I will do like this, that I will take a resistance and this circuit I will make like this. Got the point? And here I will keep it shorted. So, here you connect T, this is R, this is L, and suppose initially the switch was in the off position, there was I 0 minus was 0, etc. Then what I do, we connect the switch at position A first at t equal to 0. S to position A. Then this is a series RL circuit I t, this is E, and then current expression we know it will grow up like that. We have seen this, that is E by R into 1 minus e to the power minus t by tau, also good. Tau is L by R, time constant of the circuit. Now, one good thing about charging an inductor with a resistance in series, what will be the final energy stored? Final, if you keep the switch just like that for sufficiently long time, final energy stored in the inductor will be half L I square, is not, this much of energy will be stored, joule. Now, one good thing of this circuit compared to charging an inductor like that, I mean, I want to make several points. When I was charging an inductor just connecting with a battery, the response of the current when S is connected to A was just growing like this. But here this current will reach a finite value, even if you connect it here. Therefore, you select your R such that E by R is the rated current of the inductor, and you do not run the risk of exceeding the rated current of the coil. Of course, that current also should be the rated current of the resistance, that is fine. But here it was growing, but here it is going like this, E by R. Anyway, this will be the stored energy in the circuit. But if you keep S in position A, because after you wait for several time constants, because we will see that in our practical circuits the time constants, typical values of the time constants will be in milliseconds. Wait for few milliseconds, then you can say okay, current in the inductor is E by R. Then what you do here for this circuit I am telling, here what you do, at t equal to some time you move the switch to position B, S is moved to position B of this circuit. This circuit I am not talking, we have discussed at length. So, if you move to position A, it will be like this, is not? And this current we have seen it is equal to E by R when the next switching was done from A to B. So, at whatever time, of course, you have I presume that you have waited sufficiently long, so that the current has reached E by R, E by R was the current. Then you suddenly moved A to B. Then at whatever time you do that, current through the inductor is continuous, immediately after that current has to be E by R. Not only that, then the applied voltage is 0 and that current has to remain constant to E by R level. That is, the same thing is achieved now with this LR circuit. Inductor does not care how you pumped current in the inductor. It knows that if I am carrying this much of current, I am storing this much of energy. What is the extra circuitry that you have made to pump current into the inductor, it does not matter. Matter is how much energy it is storing. And that energy, then if you want to avoid the unnecessary power loss in the resistance, you can make a circuit like this. Okay, charge the inductor, then move this to this, and when suppose you do it, this next switching you do. So, this switching is done at t equal to 0, then this next switching A to B you do at say t equal to t, which is after sufficiently long time. Then the current through the inductor will be once again E by R and circulating here without defying any of the common rules. Okay. Therefore, this is the charging of an inductor, and I thought I will tell you about capacitor in this lecture. It is not possible. Then in the next class, I will talk about discharging of an inductor and then about deeper look into the another energy storing element, that is capacitor. Thank you.